Hi, Gerhard.
Hi, Paul. Thanks for the introduction, and yeah, thanks for having the opportunity to discuss this quite hot topic, I would say. We had yesterday lots of questions, discussions already on that topic. Let me show you. Still, it does not flip here. What's up? No, now it works. Yesterday, you heard a lot of here the basic lipidomic workflows, and also here on identification of lipid species. And this talk, I would love to focus here on quantification of lipid species. And I decided to do that with the following outline. Yeah. Most of us use here electrospray ionization for the quantification. So that is the first part of the talk. What is necessary to come to get accurate quantification? You need these corrections, type 2, type 1 corrections. And you need to consider here a species response. And then I would love to discuss here, is co-ionization crucial or not? I think we have some data concerning that question, and at the end some remarks to pre-analytics, and somehow I decided to discuss with you our setup, because I'm most familiar with that. What is our aim with the lipidomics? We want to be quantitative as far as possible. Want to achieve high throughput because we want to analyze here large clinical cohorts. You will see that we are great fans here of direct MS. We use flow injection analysis, tandem mass spectrometry, and also high resolution mass spectrometry. But for sure, you cannot cover all the lipid classes with that. So it's necessary to use also LC coupled methods. And basically, you can use it for a lot of sample types. And I have shown you yesterday also, you can nicely monitor here lipid metabolism and transport by introducing stable isotopes. So that was our first machine. It's a triple quadrupole system, Quattro Ultima, still in operation, I have to tell you. And we use it here for the main glycero phospholipids, sphingolipids. We had here a derivatization for the free cholesterol, because we heard already that is not nice, good ionizable with the electrospray. And Marcus in our lab here introduced here the high resolution instrument. It's a Q executive, and there you can get also free cholesterol without derivatization. It's very low abundant, but it works, and we can also cover here these most of these lipid classes by that approach with a high resolution machine, and we have also LC methods, especially for the minor glycerophospholipids, sphingolipids. It's mandatory, because you will not achieve here sensitivity to get these lipid classes, or you will also need to separate some isomeric lipid classes. We heard also yesterday BMP, PG. You can not get that by direct MS methods. You need to separate those, or bile acids. That is an example I would love to discuss with you. So for these isomeric lipid classes, you need a separation. Otherwise, you will not be able to get them separated. So electrospray. Why do we need internal standards for quantification? All of you know that this process is matrix dependent, which means it's sensitive to the content of these small droplets. Which kind of additives, which kind of other analytes are in these droplets, they influence this kind of ionization. So let me show you some slides from this pretty old study from Pentti Sommerharju's group, and they investigated in quite a simple way different phospholipid classes and the effects of solvent composition and also the different type of lipid classes. And you can easily see that different lipid classes show different response in here negative ion mode and positive ion mode. You see some are show these are equimolar mixtures, much higher signals than others. So you can easily modify these responses by adding, for instance, here base. Yeah, you will see that boosts, for instance, here the PA, and yeah, you can get rid of, for instance, here from sodium adducts. So you can really modify the ionization quite a lot in by adding here these modifiers. And this is also a concentration dependent response. Yeah, if you get too high concentration, you see signal does not increase linearly, yeah, in these mixtures. But a good message is if you do here response normalization, in that case it's the PC 260. You see concentration or the relative intensity behaves quite linear in a broad range. So what does it mean if we want to get quantitative results? Yeah, we have to face all these problems. Yeah, the one is here the matrix effect, and this effect depends here on solvent, additives, concentration, and also the other analytes, and influences directly our ionization response. Yeah, this response is dependent. It's also, I will show you on the next slides. Not each of the lipid classes behaves similar, but in principle, we have chain length and a number of double bonds as influence factors. Yeah, and of course, each lipid class is different, and this may not only influence here the ionization response, but also fragmentation behavior. So altogether, because frequently we use here tandem mass spectrometry, you will get differences in the analytical response of your lipid species. So in an ideal world, you have an internal standard which behaves very similar in all these respects. Yeah, and you can imagine this internal standard can only behave similar if it's co-ionized. Yeah, this is already some kind of hint to our big question. Yeah, if this internal standard is not in the same droplet, he cannot compensate for these effects. Yeah, that is what we should keep in mind. So what do we need if we want to do so-called relative quantification? Yeah, we have a sample, we add internal standards, and yeah, I think it's common sense that we have for each lipid class at least one internal standard. Yeah, it depends on your method you are using, whether you use multiple of these internal standards, but you should at least have one for each lipid class. And you extract your lipids, you analyze, and in the first step, you do these ratio calculations. Yeah? This means analyte to internal standard ratios. This is, Maria explained it already. This is relative comparison. And if you want to do some or get some quantitative estimate, you can multiply that with the internal standard concentration, so you get a nanomole value for that. If you want to do it more precise, you need calibration. Yeah? Bob told you already yesterday. How do we do a calibration line or generate a calibration line? We spike, we add lipid species in at several concentration levels. We can do that in a blank sample, but preferred it's certainly the matrix, yeah, or your you are analyzing. Yeah, for instance, if you're analyzing plasma samples, you can add on these species to plasma matrix and generate a calibration line with that. So you will analyze within each batch here the samples and the calibrators, and use the same internal standard for all these samples. Yeah, same lipid extraction analysis, calculation of that ratio, and then you can generate these calibration lines and use it to quantify, to get a so-called absolute quantification if you have really the species of interest added. In most of the cases for the bike lipidomics, we have not all these species available as reference compounds, as really with the precise concentration. We frequently use one calibration line for multiple species to calculate. If you target only a few molecules, you will have them as internal as really as standards, as reference standards, and so you can use it really to get to very accurate concentrations. So what are the requirements for internal standards? Obviously, they should match lipid class, not present in the samples of interest. Yeah, chain length, double bond content should be similar as for the analytes, and it would be good if they are cheap. This is what we are using in our flow injections. So you see PC, it's a 2804440, for instance. We use two of these internal standards because this allows us to calculate the ratio between these internal standards. And if this ratio is not constant within the batch, and we have some outliers, we have some indication that something went wrong with that sample, for instance. Yeah, so but you see we have these internal standards for all the lipid classes. And yeah, I told you this is to have two of them, you can here control the response in the individual samples. Calibrators, similar, they should cover the chain length and double bonds of your analytes, and different bond types should be also covered. This is a set of calibrators we have here in our flow injection methods. Yeah, let me show you for the PCs. We have a 34.1, 36.2, 38.4, 40.0, and also an alkyl species. And they are spiked to the sample matrix. Yeah, I told you, for instance, to plasma, and this way we generate calibration lines, and we use here the similar. We use it to calculate concentration for similar species. Yeah, and if you spike that on the sample matrix, you have the advantage that you include matrix effects. Yeah, you can somehow compensate these effects, which you would not be able if you use just a blank matrix. Yeah. So this is how it looks like. Oops, sorry. How it looks like. We need internal standards to calculate a ratio analyte to internal standard. And then we have calibration line, and this allows us to get concentrations for our analytes. What is necessary to get accurate concentrations? Yeah, this is some repetition also from yesterday. I already discussed with you the type 2 overlap. But also it's also necessary to consider this type 1 effect. What is it? It's simply the here the isotopic pattern. Yeah, if you here in that examples look at the triglycerides here, 48.1 and 58.8. You see, if you have an increase in carbon number, of course your +2, your isotopic pattern shifts to the these higher isotopic peaks. So you get in fact a decrease of your monoisotopic peak, and usually you use your monoisotopic peak to quantify. So that is quite simple to correct, because you can calculate this isotopic pattern and just calculate an effector which you can use to correct this intensity here. But yeah, you should use it. And also some Morse analyzers will have different response depending on the m over z value. So this should be also considered, but this is just yeah, biological effect, yeah, for a biophysical effect of this carbon 13 content, this natural. And that's it. A second effect resulting from this isotopic pattern is this overlap I discussed yesterday with you, and you may separate that or resolve it by high Morse resolution. And obviously, as discussed yesterday, you need to correct for that. If you're not resolve, and this correction is not is absolute requirement if you have co-illusion of your species, you need to correct for that, and it could be done in a stepwise manner. So I had this slide also yesterday. If you have high resolution, yeah, you have to check whether the Morse resolving power of your instrument is able to resolve this type 2 interference. And this is our setup, so we can for sure not resolve it for the triglyceride species. So Marcus in our lab checked how we can get accurate quantification despite this overlap. And some of you may know that this yeah, FTMS, or these orbit traps, or FTMS in general, may have problems with near isobaric peaks, and that is here the case. And you see here comparison of simulated and detected isotopic profile or peak profile here. And you see for the LISO PCs, we get quite good yeah, overlap of the simulation with the expected with the measure profile. But for the others, you see we get here a decreased, yeah, peak intensities, yeah, for the cholesterol esters, sphingomyelins, and also for the TG, and these are known effects. This is a peak interference, may be related here to the peak deconvolution algorithm in the FTMS. Marcus therefore tried different calculation methods or quantification methods, which means he uses these peak intensities without further correction. He applied a type 2 correction, which we use for which we are used to from the triple quad data. And we also tried the first isotopic peak, to do a quantification, and this is based from suggestions from Xianlin Han, because here you have lower isotopic interference in this double bond series. And he also did yeah, that for several cases. I want not to go into details. It is we call that a kind of a peak constellation case 2, case 1, case 2, and case 3, depending on the OPEX of the two isobaric peaks. Let me cut that a bit shorter, just to show you the data for sphingomyelin. And here we have the situation that obviously we have some kind of a peak resolution, but not really a good one. And if you see the different concentration, the dashed line is the target value. You see that without correction, yeah, these are the triangles. you get reasonable values for lower spike concentrations. Means in that range, but for higher concentrations, you end up in too low concentrations. So there, it's obviously better if you use here the +1 isotope for quantification. You get much more accurate concentrations, and obviously type 2 correction is you get wrong. It fails. Yeah, you overcorrect here in that situation. Marcus summarized that into that scheme, which applies here for peak resolution. Yeah. And you see here, if you have sufficient resolution, you have to, yeah, for sure, no correction is necessary. In that range, which is in our setup, it's Q Executive with 140K resolution at 200 m/z. Some interference starts here, especially in that range about 680 mZ to here 9,000 mZ. There it turned out that the M+1 base quantification is superior to uncorrected, and type 2 correction, you need a pretty good overlap. Yeah, this is would be here in the higher Morse range necessary. But there we were quite surprised that, because you can remember the triglycerides, they show one peak, but if you use here type 2 correction, you simply overcorrect. So you should, a key message, you should figure out these type 2 overlaps in your instrument platform to evaluate the best way of correction or quantification. And that is really yeah, key hurdle to get to accurate quantification in lipidomics data. So what else could be a problem? For instance, if you think of positive ion mode, you may get an isobaric interference of different adducts. I told you already, this is sodiated adducts here for the PC36-1. This could overlay or interfere with the protonated PC species here with 2 additional carbons and 3 additional double bonds. You see, this is a very small mass difference. Yeah, just 2 millidalton. So with our instrumental setup, you are not able to resolve this. These peaks they perfectly overlap, and therefore you can do a kind of type 2 correction we used from the triple quad. So you calculate actually for the internal standards the ratio protonated to or sodiated to protonated peaks, and that ratio is used to correct, yeah, these data in positive ion mode. And if you don't do correction, for instance, you see here the PC. This is plasma data. I think these are, yeah, several hundred data points. And you see the mean values here, and without correction in positive ion mode, you would have an overestimation, for instance, here for the PC 38.7, yeah, because this results here from the PC 36.3 or and so on. Applying that kind of correction algorithm, you can really match here the references. You can measure also in negative ion mode. Marcus did that here in that case. If you compare negative ion mode as reference data to the positive ion mode data without correction, you see huge overestimation here for the PC 38.5, but after correction you get quite a good match with the negative ion mode data. So that may be a way to compensate such interference. So what else is necessary? to get to accurate values, you need to consider a species response. Bob told you that already yesterday, and we have here different lipid classes. Yeah, here the PC. These are the calibration lines from our triple quad instrument, and you see we get really very similar responses for all these different species. So that behave quite good in that respect. No, not much difference concerning chain length and double bonds in here in positive ion mode. But if you have a look at cholesterol esters, you see huge differences. Yeah, here it's MS procedure. Marcus evaluated that also here for in our FTMS method, and he used here yeah, C17 zero cholesterol ester is as internal standard, and yeah, used different standards. Yeah, here in variation of chain length. Yeah, just saturated species. You have monounsaturated species, and the most pronounced difference he observed is in if you add double bonds. Yeah, here it's a C18 species, saturated, monounsaturated, diunsaturated, and three double bonds. And you see it increases hugely the response of the cholesterol esters. You see here it's just plotted the response of the C18 cholesterol esters. And what is the reason? One reason for that is that these cholesterol esters generate in source here the cholestadiene. So they lose here the acyl moiety. And if you add here double bonds to the acyl part, you may stabilize, yeah, that molecule, that ion, yeah, and so you see for these unsaturated species that you get much more intact yeah, ammoniated ion in comparison to this cholestadiene fragment compared to the saturated species. Yeah, it's just a stabilizing effect. And Marcus calculated here a model for response correction of these species, which uses here carbon number and a very important term, the number of double bonds, and also a matrix factor. And if you compare here the enzymatically measured total cholesterol, which is here in the clinical chemistry routine used, so it's a sum of free cholesterol and cholesterol esters, and you compare that to the FTMS derived values, you see without correction you get too high values if you use here the mass spec method. But if you apply that correction model, you get quite good a match of the concentration. So obviously it's necessary to correct for these responses. Yesterday, we also had some questions about quantification in tandem mass spectrometry in negative ion mode. If you use here the acyl fragments, and that is a quite complicated task due to the fact that here the response of these acyl chains depends on the SN positions. Yeah. Here you see you get higher response from the SN2 position, yeah, of these standards. And already yesterday there was mentioned that here Andrei Shevchenko's lab came up with a model. Kai Schumann in Andrei's lab developed here a model for these response corrections, because you see that you have not only SN position, but you have also the chain length has an effect in the response, as well as double bonds. Yeah, a higher number of double bonds, you get a decrease in relative intensity, and also double bond location has an effect. Yeah, and they summarized it to here a computational model, and looks like that with a fatty acid index, and yeah, here yeah, normalized collision energy. And if you use, they compare the direct measurement by FTMS before and after correction. So you see that you, without that type of correction, you will fail, especially if you have polyunsaturated species. Yeah, you are far off the FTMS measurement, but if you do that type of corrections, you get it, and you have to keep in mind that it's a logarithmic scale. Doing quantification in MS2, especially if you use here the ASO fragments, could be quite difficult. So it needs probably here good models to address that type of response differences. So now to the question: is it really relevant to have co-elution or co-ionization also of your internal standard and your analyte? So I think Michael discussed already yesterday with you that it's really superior to have that situation, to have the internal standard and the analyte in the same droplet and same conditions to ionize that. And I pointed that out already in the first part. That is simple chemical analytical chemistry. An internal standard which is not in the same droplet, it cannot compensate in an accurate way. And obviously, if you use reversed phase chromatography, you will have a non-polar selectivity. So you will have your different chain lengths spread it in a wide range of retention times. So this is obviously beneficial if you want to separate isomers, but in terms of quantification, that is a difficult situation. And there is maybe one solution. You could use a stable isotope labeled internal standard. We heard it multiple times. This is the gold standard for each individual species. So you get perfect situation. There are these standards are generated, and there are investigations. I think in Vienna, Harald Schöni and has this Lilly internal standard, for instance. So that is some kind of solution to that situation. Otherwise, it's difficult, and I would love to show you also some data on that. Just as an example, we have here the Helic method in our lab for LPA and sphingosine 1-phosphate, and you see Helic allows here in a perfect way co-elution of internal standard and analytes. And let me show you here this example from our clinical routine diagnostics. So we do quantification of bile acid species for diagnostic purposes here for our pediatrics department. Here they do liver transplantation, so they are interested in these bile acid species of their patients. And we had that situation in the routine that there were no Tauro conjugated internal standards available at that time. We developed the method. The method is just a simple acetonitrile precipitation, but we have internal standards, stable isotope labeled internal standards, basically for all analytes except the Tauro conjugates. These precipitate or the protein precipitated samples, they were subjected to a reverse phase chromatography to separate the isomeric species. And we had not good precision here for the Tauro conjugates of our controls. But then they were commercially available. We bought them, and Sabrina in our lab here investigated the performance in detail. If we compare the results with the gold internal standard, so it's a D5 labeled here in that case TCDCA. And obviously you have almost perfect co-elution. of your analyte and your internal standard. And this is the controls, quality controls, and you see quite good precision, accuracy we get here for this when we are using that. This is, I have to say, I think 13 different batches. And Sabrina now did calculations using simply other internal standards. So here you see, in that case, she used another here Tauro conjugated, but it's an isomeric compound. It's a DCA, and you see you get not only higher variation in your controls, but also a shift in accuracy. And she did it not only for the quality controls, but also for the patient samples. And there we used the values determined with the matching internal standard as the reference. And you see you get similar shift and a variation. But you see this is 50%, or you may miss it up to 50%, the accurate value. She did it also here for a glycoconjugated internal standard, which has close co-elution to our analyte, and that one was the internal standard we used before. You see you get not so good CVs, and also quite more variation in the values for both controls and patients. And finally, she checked if you just use here counts without internal standard, basically. And there you see it's getting wild. You get here twofold miss the values. So this is clearly indication that an appropriate internal standard is mandatory if you want to do a precise quantification. So if you have here the chance to get here a labeled internal standard, you should invest that money. And if not, co-elution may be beneficial, but you see a small difference here. It's just glyco instead of tauro. You may not get so good results. But if you have, for instance, no internal standard, it's very difficult to get a really good quantification. So let me end with some remarks to pre-analytics. And you heard already for in Junken's talk, that LPA it's quite tough concerning pre-analytics. We had also this experience. Just one remark: if you have similar problems with the sphingosine 1-phosphate, so it's whole blood. If you leave it at room temperature, you see several fold increases within hours. And you may stop it here for the sphingosine 1-phosphate if you separate plasma, but not for the APA. But you heard Junken, they have sophisticated recommendations for LPA stabilization. Here this is quite recent data from our lab, from Sabrina and Alex in our lab. They investigated here tissue homogenates in methanol waters, and we came to that observation because we had control samples prepared in this organic mixture. And so they are quite unstable. They were repeatedly freeze thawed, and for ceramide, it were liver homogenates. They were quite off, despite we kept them cold. And this was a bit to our surprise, because we thought, here 50% methanol, this stabilizes somehow samples, but it does not. If you have a look here on these lipolytic ratios, for instance, ceramide, sphingomyelin in liver samples, this is here the situation that you get here immediate rise. This is storage at room temperature, a twofold increase of the ceramide sphingomyelin ratio. And this was turned out to be the most sensitive parameter in different tissues. Here's brain, lung, heart, spleen homogenates. And we tested here SDS as a stabilizer, yeah? And you see in most of the tissues it worked quite well to add some here SDS to stabilize these samples. So, but this should be just a remark that you can not trust that your samples are stable, adding here some kind of organics. Yeah, the lipolytic activity, especially here in the liver, this is quite high. Yeah, or also here in heart, you see similar effects. And if you want to investigate, you may use this such kind of ratios. Yeah, for instance, also lyso PE to PE. You see, immediate rises, and you may stabilize this, for instance, also in the heart. So to summarize all that, what are important factors for quantification? Yeah, it's the internal standard, obviously. Yeah? Is it matching the lipid class, or is it even matching here the lipid species? Do we have co-ionization of analyte and internal standards? I think that is just analytical chemistry, that it's a quite important factor. Did you consider the analytical response in your settings? This could be done by calibration line or response factors. And even similar importance has here pre-analytic considerations. Yeah, if you, how are the samples stored, homogenized, and I told you here, lipid identification, you have to consider here, obviously, these isotopic, isomeric, and isobaric interferences or in source fragmentation could be, could change your results. And if you do assay development and quantification, you should evaluate reproducibility, accuracy of your assay, limit of detection, the dynamic range, and sample carryover. And yeah, so with that, I would like to acknowledge here the people in the lab, yeah, Marcus, Sabrina, and also Alex did a great job, and yeah, our collaborators. And yeah, thank you for your attention. And yeah, I mentioned already, we have a conference here in October. I would be happy to see you. And yeah, I'm happy to take your questions.